So we have the integral of dx over cosine squared 2x. Any thoughts on how we can go about this one?
Make it secant squared 2x.
All right, that's a good start. So we're going to make this an integral of secant squared 2x dx just by using our trig step. Whenever cosine is secant, so whenever cosine squared 2x ought to be secant squared 2x. And then we do know the integral of secant squared of x dx, right? What's the integral of secant squared x dx? Tangent. Tangent, right? But since we got a 2x in here, that's a little bit of an issue. So what do we have to do to get rid of that 2x?
U-Substitution.
Yeah, so let's just get rid of that 2x, making it u. U equals 2x. And if u is 2x, what is the du that we need? 2. Should be 2, and then, 2 dx. And we don't have that 2, right? We just have the dx. So we will have to put into that. It is going to give me my tools. There we go. We'll have to put in a 2. And if we put in a 2, we have to cancel out that 2 somehow. And how do we cancel out that 2?
Multiply the whole thing by 1/2.
Multiply the whole thing by 1/2. So we'll put that outside. So now we have 1/2 of an integral of secant squared u. Secant squared 2x is secant squared u. And then the 2 dx is just du. 1/2 of the integral of secant squared u du. Everybody good there with that?
Yes.
And that should just give us 1/2 tangent u plus our constant, which ought to be 1/2 tangent 2x plus our constant. Good or no?
Good.
Any questions on that one? All right, let's do another one. Look at that. Making great time here. Cotangent squared 3x dx, the integral of that. What are we going to do?
Replace 3x with u.
Okay. So u equals 3x, which tells us that du will be
3.
3 dx.
I have 3 dx.
And so that means that we're going to put a 3 inside of here. And if I put a 3 inside of there, that means we need to put a 1/3 on the outside. Everybody agree with that?
Yeah.
Mm-hmm.
All right. So we've now got 1/3 of the integral of the 3 dx becomes the du, and then cotangent squared 3x becomes cotangent squared u du. All right, so do you have a rule for cotangent squared of x or cotangent squared of u on your integral rules sheet? I'll save you some of the time there. No, you don't have a rule for that. So that's a problem. So anybody have a good idea of how we can deal with cotangent squared u? All right, no ideas on that. Think about the ancient Greeks. Are you thinking about the ancient Greeks? That's going to help you. That's why I'm telling you to do that, to think about the ancient Greeks. Aha, and now you see it. right?
Yes.
Great, so what do we do?
You change cotangent squared.
Okay, yep. How so?
Either, can you multiply the whole thing by its inverse and make it tangent squared?
No, no, you can't.
Then break it up into sine squared and, wait, no, cosine squared and cosecant squared?
Sine, it would be cosine squared and
Cosine,
cosecant
yeah.
squared.
Cosine squared over.
But what's the reason you want to do that? Give me your ancient Greek reasoning for that.
Maybe we could change what u is equal to.
Nah, I like our u. Our u equals 3x is good.
Can we use the Pythagorean theorem?
All right. Sort of, the Pythagorean theorem. It's one of our Pythagorean trig identities. So that's our ancient Greek. You figured it out. Pythagoras. Hooray. The ancient Greeks. So what are our Pythagorean trig identities? We have sine squared plus cosine squared equals 1. Well, that's not this one at all. And then we have 1 plus tangent squared equals secant squared. Well, that's not this one either. And we also have what? What's the third Pythagorean trig identity that you are all familiar with, have memorized, and know how to utilize properly?
Cosecant minus 1 is cotangent.
Normally we have it written this way: cotangent squared x plus 1 equals cosecant squared x. I'm not sure if that's what you said, because the first part of what you said cut out for me, but cotangent squared x plus 1 equals cosecant squared. So that tells us that cotangent squared should be equal to
Cosecant squared minus 1.
cosecant squared u minus 1 du. Does that help us? Do we know the integral of cosecant squared u?
Negative cotangent u.
Should be negative cotangent u. Yep. So we know that one, and then the minus 1 should be easy. So you should know there's 6 antiderivatives on there, right? There's the antiderivative of sine, the antiderivative of cosine, of secant tangent, and cosecant cotangent. And then there's also secant squared and cosecant squared. So if you can turn the function that you have into one of those things, try to do that, because you know those integrals. So this one should become 1/3, and then the integral of cosecant squared u is negative cotangent u, and then minus u, and then plus our constant. Everybody good with that?
Yeah.
All right, and so we end up with negative 1/3 cotangent 3x, and then we've got a minus 1/3 u. Well, that'd be minus 1/3 of 3x, which will just be minus x, and plus 1/3 of our constant is just a constant still, so plus a constant. Good or no? Any questions, issues, complaints, concerns? No?
Where does the, oh, never mind, I got it.
Okay. Any other questions or almost questions about that? All right. How about cosine cubed x dx? Any thoughts on that one?
Well, we don't have to replace x with anything, so we can just jump to integral, to taking the integral of it, which, oh wait. Actually, it's, oh, this time it's cosine cubed.
Yeah, cosine cubed. So that one's makes it a little more difficult, right?
Yeah.
Yeah. We don't have a formula for cosine cubed, and I can't offhand think of a way to turn cosine cubed into just cosine or just sine or
I guess you can,
tangent or cosecant cotangent or secant squared or cosecant squared.
wait, can you simplify it to like, does simplifying it to cosine squared x times cosine x work?
Well, it'll do something, and that will be our first step. So let's make that cosine squared x times cosine x dx. Why might we want to do that?
Because that way it makes it easier to take the integrals of them.
Mm,
Like you can take the integrals.
you can't take the integral of this as it is right now, because it's still cosine cubed x. It's still a multiplication between these two terms here. But what it does do is it does allow us to go back to ancient Greece again. This is going to be my theme for the day, perhaps. Well, maybe not for the day, but at least for the last problem in this one. Let's go back to ancient Greece again. That'll be fun. And what can we do with cosine squared?
1 minus sine squared x.
All right, so this is 1 minus sine squared x times cosine x dx now. And so now we're almost there. We're almost finished with this. I almost have it ready to integrate. What should I do? All right, let's go back to this one. What did we do in this one? We had to do what? Forget all this stuff down here. What did we have to do? Forget everything below the line. What did we have to do?
A U-substitution.
We had to do a U-substitution. What do we have to do here?
A U-substitution.
What did we do on this one? When we did this like the other day.
A U-substitution.
Ah, yeah. What about this one?
Probably a U-substitution.
Yeah, definitely. What about this one?
And a U-substitution.
Ah, nice. Yeah. You guys see the pattern? What do you think we should do with this one?
U-substitution.
Ah, good thinking. Yeah, nice work. All right. So what should our U-sub be?
Cosine x.
All right. So let's think about this. Or let's do this and see why this becomes a problem. Let's let u equal cosine, right? So then du will be negative sine x dx. So the cosine x is easy enough to get rid of. Now I've got a u there instead of that, right? U. Well, what about 1 minus sine squared x dx? That's not what I have here. I have negative sine x dx. So I can't replace this negative sine x. There's no negative sine x dx to replace with a du. So that u substitution is going to be a little bit of an issue. Cosine's not going to work out. Any other thoughts on what you'd like u to be?
1 minus sine squared x.
All right, let's look at that one and see why that one doesn't work out. So if u is 1 minus sine squared x, du is the derivative of that. The derivative of 1 is 0, right? That goes away. But the derivative of negative sine squared x is negative 2 sine x times the derivative of sine x, which is cosine x. So I can get rid of this, and I've got the cosine x dx part, but then I still need an extra negative 2 sine x in there, which is going to be an issue. So we got to find something that when we sub it out, we're left all in terms of u, except with just the du attached to it. So clearly the 1 minus sine squared didn't work and the cosine didn't work. So I don't know, what else? What else might we try?
Sine squared.
All right, let's try sine squared. So if u is sine squared x, that's going to give me 1 minus u. That's fine, right? And then du will be the derivative of that, which is 2 sine x cosine x dx. So I got the cosine x dx. But what about that 2 sine x? That's still a problem again, isn't it?
Mm-hmm.
Yeah. Other thoughts?
Could you just make it sine x?
Let's try it. If u is sine x, then this is what? 1 minus u squared, right? And what's du? Just cosine x dx. Ah, that seems like that's a good idea. There's cosine x dx. That's my du. So this just becomes 1 minus u squared du. And 1 minus u squared is easy enough to integrate, isn't it? So
Yes.
don't get too complicated with your u subs. Sometimes a nice simple function to sub out might just be, might just be enough, right? You don't need to do the full 1 minus sine squared, or just the sine squared, because it's still going to put it in terms of something that I can integrate easily if I just get rid of the sine. And so what is the integral of 1 minus u squared?
Where did our cosine go?
Our cosine goes away. Cosine x dx is du.
Oh, okay.
Yep. Good?
Yeah.
Okay. Any other questions on that so far? Everybody okay with that to this point now? All right. What do we get when we integrate then?
U minus u cubed over 3.
U minus u cubed over 3 plus your constant, and then we'll just replace the u's with sine x. So we got sine x minus sine cubed x over 3 plus a constant. Any issues with that? Everybody okay with that?
Yeah.
Cool. No questions, everyone's good. All right, let's take a look at this one. The integral from 0 to pi over 3 of tangent x times secant squared x dx. What do we think? I know what you're thinking. You're thinking, how cool would it be if we did this one 2 different ways? That's what you were thinking, right?
Wait,
Yeah.
just to clarify, what exactly is a 0, like the sub-zero towards very bottom supposed to?
That's the integral from 0 to pi over 3 of this.
Oh,
This is a definite integral.
yeah, all right.
So any thoughts on how we're going to integrate this? It's not secant tangent, right? Because it's secant squared tangent. That'd be really cool if it was secant tangent, because then it'd be really easy, but it's not. And it's not just secant squared, because that'd be really cool, because that one I can just integrate. Got tangent attached to it. So any thoughts on this one? I don't know if you guys have noticed, but in math, there are a lot of patterns. So let's see. What do we do with this one?
A U-substitution.
Ah, yeah. Let's see. What did we do with this one?
U-substitution.
Yeah, good. What about this one?
U-substitution number 3.
Ah, yeah. And wait, what about this one? And this one?
Substitution.
And this one? Oh, yeah. So what do you think we might want to do with this one?
U-substitution.
Nice. All right. So what do you want to sub out?
Tan x.
Okay. Seems like a reasonable choice. If I let u equal tangent x, what is du equal?
Secant squared x.
secant squared x dx. All right, so now as I go in here to rewrite this, tangent x is now just u, and secant squared x dx is now just du. So I just have the integral of u du. That's going to be a pretty easy integral to do, isn't it?
Yeah.
All right, now we have one little thing that we got to take care of here, though, that is different now because this is a definite integral. What can you tell me about pi over 3 and 0? What variable are those representing?
X.
Those are representing x, exactly. And now down here in this integral, everything in my integral is in terms of u, which means that I need to get rid of these x values and turn them into u values. So we're going to say, what is the tangent of 0? So if x is 0, what does u equal?
0.
0. So we're going to say it down here. And you don't normally need to write the u equals 0, but I'm going to do that just to illustrate why I'm changing these limits or not changing them in this case. And what about the pi over 3? What does it need to become? What's the tangent of pi over 3?
Square root of 2.
No.
Like,
Root 3.
Root 3. You guys should all have all of those memorized. All of the unit circle values. All right, so now instead of integrating from 0 to pi over 3, we're going to integrate from 0 to root 3 of u. And the cool thing about these, about definite integrals when you do u substitutions is, let's see, when I integrate this, I just get u squared over 2, right? Since I converted these from x values to u values, I don't have to convert back to x. I can just evaluate this in terms of u, and I'll get the same answer. So what do we get if we evaluate this from 0 to root 3? Should be root 3 squared over 2 minus 0 squared over 2, right? Which is what?
3/2.
3 over 2.
3 over 2. Good or no?
good.
Great. All right. Now, I said we were going to do this one a second way. So let's see. What did we do here? We did a U substitution, right? Do I need to go back through and point to all the other ones and say we did a U substitution on them again? Probably not this time. I want to do another U substitution, but I want to do a different U substitution. So anybody have a preferred U substitution other than tangent that they think will work nicely?
Secant squared x.
Okay. So, sorry, did you say secant or secant squared?
Secant squared.
Okay, so let's look at secant squared x. If I do u equals secant squared x, that's going to give me du equals 2 secant x, and then times the derivative of secant x, which is secant x tangent x dx. So I'm going to have 2 secant squared times tangent that I need to get rid of. And I'm also going to have a secant squared in there. And so what do we think about that?
Too messy.
Too messy. Well, actually, what do I have? In fact, I've not actually done this problem using secant squared. Normally, I've just used secant because it cancels out really nicely. But this happens to look like it might actually work out really nicely because what's my du? It's 2 secant squared x tangent x. Well, I have a secant squared x tangent x. And all I would need in there would be a 2 to get rid of the everything in there to just make it a du, right? So could I try to do this? Put a 2 in there. And put a 1/2 on the outside. And what would that become? Instead of going from 0 to pi over 3, we'd have to go to secant squared of 0. Well, what's the secant of 0?
One.
1. So we'll go from 1 to what's the secant squared of pi over 3? What's the secant of pi over 3?
Um,
2.
Secant of pi over 3 is 2, so secant squared of pi over 3 ought to be 4, right? And so now what happened when I did all of this substitution? I have 2 secant x tangent x dx. So I just have a du inside of here, or effectively I have a 1 du, right? Du is just 1 du. And so what do I get if I integrate du, or 1 du? What's the integral of 1?
U.
U.
It'd just be u. And so what do we get here? We get 1/2 times 4 minus 1. Well, what does that equal?
3/2.
Should be 3/2. Okay, now the good news is today we have lots of time. So we're going to do this a third way. Let's suppose that we let u equal secant x. Then what would du be? What's the derivative of secant? This is the easy
Tan.
secant x what?
Tan
Tan
X.
X.
All right. And so if we go back and look at this integral, I have a secant squared times a tangent, right? So that's secant times tangent. Well, the secant will be a u, and then the secant tangent will be my du. So that's going to give me an integral of u du. And now instead of going from 0, I'll go from the secant of 0, which is 1, to the secant of pi over 3, which we just said a minute ago was 2, right? And what does that give us? It gives us u squared over 2 from 1 to 2, which gives us what? 2 squared over 2 minus 1 squared over 2? Or 2 minus 1/2, or 3/2. So we can see that no matter which U-substitution we chose, they all still come out to give us the same numeric answer, right? So they all come out to give us 3/2. Good or no?
Good.
All right. Now, that was all really exciting, wasn't it? We did the same problem 3 different ways and got the same answer.
And
Y'all
bigger.
find it very exciting. Yeah, of course you did. I want to do this problem. The integral of secant squared x tangent x dx. It's the same problem, right? Except that this time, what?
Infinite integral.
Yeah, it's an indefinite integral, right? It's no longer a definite integral, it's an indefinite integral. There's no limits of integration. So which way do we want to do it? Do we want to do it with the secant substitution, the secant squared substitution, or the tangent substitution?
Secant.
Which one?
Secant.
Secant, okay. So let's let u equal secant x. And so like we said a minute ago, du is secant x tangent x dx, right? This is all what we just did a minute ago. So this becomes an integral of, well, the secant tangent dx becomes our du, and the other secant becomes our u, and we get u squared over 2 plus our constant, right? Which would give us secant squared x over 2 plus our constant. Everybody agree that that would be the indefinite integral of this? Yes, no, maybe?
Yeah.
Yes.
All right. Cool. Now, pick a different way. Which substitution do you want to use this time?
Secant squared.
Secant squared, okay. And that gave us du was 2 secant x tangent x times another secant x, right? I'm running out of room here, dx. That's fine. So we had to do the 2 on the inside, right? And we had to do the 1/2 on the outside. And then we just ended up with 1/2 the integral of du, which gave us 1/2 of u plus our constant, or 1/2 of secant squared x plus our constant. True? Exactly like what we got here. Would you agree?
Yeah.
Yeah. All right. One more time. Let's take the integral of secant squared x tangent x and do it the other way. What was the other way that we did this? We did a u equals tangent x, right? With du equals to secant squared x dx. And so this became an integral of u du. Everybody agree there? Okay. Which gives us u squared over 2 plus a constant, just like we had when we did this one, right? U squared over 2 plus a constant. But now our u value is not secant, our u value is tangent. So this gives us tangent squared x over 2 plus a constant. Well, how can tangent squared x over 2 plus a constant and secant squared x over 2 plus a constant both be the integral of secant squared x tangent x? All right, we got 1/2 secant squared x over, we got 1/2 secant squared x, we got 1/2 secant squared x plus the constants. But this time we got 1/2 tangent squared x plus the constant. Tangent squared x over 2 and secant squared x over 2 are not the same thing, are they? I mean, if those were the same, if secant squared x over 2 and tangent squared x over 2 were the same thing, that would mean that secant and tangent were the same thing, and they are definitely not. Would you agree?
Yeah.
So what's the difference between these things then? Because clearly doing it this way with tangent and this way with secant squared and this way with secant were all okay. They all gave us 3/2, right? They all came out to be the same. But when I do the indefinite integral, they don't all come out to be the same. 2 do, and the third one doesn't. So what's the difference between 1/2 secant squared x plus a constant and 1/2 tangent squared x plus a constant? The difference must be the value of the constant. The difference has to be that value of that constant, because the value of the constant, no matter what it is, will disappear no matter which way I do it if it's a definite integral, right? Remember we said that if we put the plus c into the definite integrals, or if I put a plus c here, I'd be adding the c and then subtracting the c. So that constant doesn't matter for a definite integral, but it can certainly affect our results. It could certainly affect our answer when we do it this way. So what I've done now is I've written both of these answers out, and we're going to say that these things are equal. One of them has a constant of constant 1, and the other has a constant of constant 2. And we're going to see what's the relationship between the two constants and how they differ. that make sense to everybody?
Yes.
Okay. So what does what does secant squared equal? Thinking back again to ancient Greece.
One plus tangent squared.
So we got 1 plus tangent squared x over 2 plus our second constant. And so we should already almost immediately see that this can become 1/2 plus tangent squared x over 2 plus our second constant. And the tangent squared x's over 2, which are the same, we can get rid of, right? And that tells us that constant 1 is equal to 1/2 plus constant 2. So in order for these things to be equal to each other, constant 1 has to be 1/2 more than what constant 2 is. So if constant 2 was 7, then constant 1 would have to be 7.5 for these to be equal. And that's okay. It's okay for the constants to differ, right? And these answers, both of these answers would be good answers, and I would take either answer. And you don't have to tell me that there's multiple ways to do it and you get different things and they differ by a constant. But just recognize that there are different ways to do the problem or indefinite integrals that may result in something that looks very different than something else that is still correct. And that's one of the cool things about integrals is there might be multiple different functions that we can use that still give us the same, or still give us a correct answer that might look very different than other ways. Does that make sense? Isn't that cool?
And the same type of situation would happen if it was like sine and cosine, right?
Yeah, so potentially you could do, yeah, we could do a quick, let me see, I don't think I have one exactly like that, yeah. So like, suppose I just gave you the integral of sine x cosine x dx, right? Well, you could do u equals sine x, and du is cosine x dx. Or we could do u equals cosine x, right? And then du would be negative sine x dx. And so doing it this way, we'd have to do an integral, we'd have to have a negative sign, we have to put the negative in and out so that we could substitute out the cosine x and the negative sine x to make this negative integral of u du, which would be negative u squared over 2 plus a constant, or negative cosine squared x over 2 plus a constant. Or we could just do it this way with u as sine, and this just becomes u du, or u squared over 2 plus a constant, or now sine squared x over 2 plus a constant. And so either way you choose to do it, you're going to get two very different answers that are both correct. There's nothing wrong with either way to do it. It just recognizes that this and this are not equivalent. They differ by what the value of the constant itself is. But either one will correctly tell you the area under the curve if I throw some limits on here. So if I go in here and say, from 0 to pi, right, this will give me the same value that this will give me. Good or no?
Good.
Don't you guys all find that fascinating?
Yes.
Thank you for lying to me. I appreciate it. All right. That's good. Maybe you did find it fascinating. I don't know. But at least somebody said yes. One of the other 31 people in here besides me. All right. What should we do with this one? What should we do? Any thoughts?
A U-Substitution.
Thank you. I was just about to start going back through every other slide. So what do we want you to be?
X squared minus 4.
Okay. What will that make du?
2x times dx.
2x dx. So do I have a 2x dx to get rid of?
No.
No, but I could just put a 2x in there, right? By putting a 1/2 outside.
Mhm.
All right. So let's turn this now into 1/2 of the integral of 2x dx is du. So du over x squared minus 4 is u. So du over u. And what do we need to still do before we can figure out this integral? Because this one was a definite integral. What should we do?
Change the values.
Change the values from x values to u values. So we'll say 0 squared minus 4. What's 0 squared minus 4?
-4.
Minus 4.
Negative 4. And then 1 squared minus 4 ought to be negative 3.
3.
And so we've now just got the integral, or 1/2 the integral from -4 to -3 of du over u. And what's the integral of du over u? Because remember, you memorized all the formulas on the integral sheet in the Google Drive. Remember that? So you know that one off the top of your head really easily.
Natural log of u.
Natural log, absolute value. Yep. And we're going to evaluate that from -4 to -3. And now we can see why that absolute value becomes very important, right? Because if we didn't have that absolute value on there, we wouldn't be able to evaluate this at all. And so we end up with 1/2 of the natural log of 3, absolute value of -3 is 3, minus the natural log of 4. Good or no? Everybody good or no?
Good.
All right. This is a good answer. Potentially on a multiple choice problem though on the AP test, you might see it written a different way. You might see something like 1/2 of natural log of 3/4, right? That would work too. Using log rules, natural log of 3 minus natural log of 4 is natural log of 3/4. Or you might see something like natural log of the square root of 3/4, right? Because if you have a coefficient in front of the logarithm, you can bring it in as a power, and the power of 1/2 is the square root of 3/4. You might see that. Or you might see that simplified, natural log of root 3 over 2. You might see that. Or you might see natural log of root 3 minus natural log of 2. You can see all kinds of different ways. So just be able to manipulate these also, in case it's a multiple choice question. If it was a free response, they'd take any of those answers. But good or no? Great. All right, we got 3 more problems to do here today. 4x over root x squared plus 9 dx. What are we going to do with this one?
U equals x squared plus 9.
All right, good. If u equals x squared plus 9, what's du going to be?
2x dx.
2x dx. Do I have 2x dx?
No, but you do have 2x times 2x.
No, I have 2x times 2.
Oh, and 2x times, yeah.
Okay, so that 2x dx can stay in there, right? In fact, the 2 can stay in there if I want, but I can also pull it out to the front. Would we all agree that that's the same?
Yeah.
So now we've got 2 times the integral of, well, like we said, 2x dx is du. And then this is a square root of u in the denominator. So we could rewrite this as 2 integrals of u to the -1/2 du. And now we can just use the
Rule.
the power rule, yeah. And so what do we get when we integrate u to the -1/2? It should go up to +1/2, right? So we have 2, and then we have u to the +1/2 divided by 1/2.
Yeah.
If we're dividing something by a half, what should we get?
2.
Another 2 out in front of there. And then we should be Should be good there, right? It should just be 4 root u plus our constant. I should put my plus constant there, which is 4 square root of x squared plus 9 plus our constant. And so we can see that really what we're getting here is we're doing the chain rule in reverse, right? That's what these U substitutions all are. And this is a chain rule derivative. Comes out to be something like this. So we use a U substitution to integrate it back to that composition of two functions. Everybody good?
Yeah.
Any questions or anything before we do these last couple problems? All right. We have x cubed times the square root of x squared minus 1 dx. What do you think you should be? Better at math? That was a joke. You can all laugh. No? Okay. What should you be?
X squared minus 1.
Yeah, all right. So if u is x squared minus 1, what is du?
X squared 2x dx.
All right, so let's see what's going on here. We've got an integral of, we had x cubed, not 2x. Can I put the 2 in there? I'm putting a 1/2 here.
Yeah.
And so if I have a 2x, but I used to have an x cubed, I also need to have what in here?
X squared.
X squared. And then I've still got my square root of x squared minus 1 dx. That we'll get rid of that, x squared minus 1 in a second. So now what does this become? 1/2 of an integral of, well, the 2x dx ought to become the du. But what about the x squared? There's no x squared there. So x squared root u du. And we have a problem, right? We still have that x squared, whereas everything else turned into terms of u. So how can I deal with this x squared?
Turn it into u plus 1.
Exactly. We're going to go back up here and say, well, x squared is equal to u plus 1. And so we then should be able to say this is now equal to 1/2 the integral of u plus 1 times u to the 1/2 du. And how will I deal with that integral? Since it's two things being multiplied together, I can't just integrate it as is. I either need to do a substitution or do some algebraic manipulation to simplify that into something I can integrate. So which one sounds better?
U to the power of 3 over 2 divided by 3 over 2, which is 2 over thirds u to the power of 3 over 2.
I'm not sure what you just said. So what do we need to do with this to be able to integrate it? We have to do something with this to be able to integrate it.
Distribute?
Yeah, we have to distribute it first. So u times u to the 1/2 is u to the 3/2. And then 1 times u to the 1/2 is u to the 1/2. And now that it's all just a bunch of, variables to a power plus other variables to powers, we can just use the power rule. So this is 1/2, and then this becomes, what does the u to the 3/2 become? Should be 2/5 u to the 5/2 plus 2/3 u to the 3/2 plus our constant. Everybody agree with that?
Yeah.
Okay, and then we're going to do two things here as we write our final answer. One is we're going to distribute the 1/2 through. So half of 2/5 is just 1/5. And then we'll replace the u with x squared minus 1. So we got 1/5 of x squared minus 1 to the 5/2 plus 1/3 of x squared minus 1 to the 3/2 plus a constant. Good or no?
Good.
Cool. And you'll see a few like this towards the ends of problems 1 and 2, like 1 X, Y, and Z or something like that. You'll have to do something where you're still left with this additional term in here that we'll have to figure out how to substitute it out.
And depending on your U-substitution, might not work.
All of the ones that I have given to you should work out pretty nicely. There is times where you might think that this method will work and it won't, and you'll have to use some other method that is from a more advanced calculus class, but you won't have to do that here. You should always be able to find something that works out pretty nicely for ours.
Okay.
Yeah, with me meaning this is working out pretty nicely. I know that's not a real clean, great looking answer, but it's could be a heck of a lot worse. So, all right, last one for the day.
U equals x squared minus 1 with du equal and du equals 2x dx.
Okay. So if we look in here, we've now got, we're going to put a 2 in, we're going to have to put a 1/2 in, so those will cancel. And then we have the x, but what's left from the x to the 5th if we just have the x?
X to the power 4.
X to the 4th, and then we have square root of x squared minus 1, which is square root u dx. And then our 2x dx will become our du, but what about our x to the 4th?
X squared x squared x squared equals u plus 1, so yeah, u plus 1 squared.
Right, so our x to the 4th, that's just x squared squared, so it should just be u plus 1 squared. So we've got 1/2 the integral of, and then the 2x dx will become our du. The x to the 4th will become u plus 1 squared times u to the 1/2 du. So does everybody see how we got that to real nicely turn into all terms of u?
Yeah.
Any questions on that from anybody? Okay. All right, so u plus 1 squared, that's gonna, the first term of u plus 1 squared is u squared, right? And u squared times u to the 1/2 ought to be u to the 5/2. The second term of u plus 1 squared ought to be 2u. So that ought to become 2u to the 3/2 when I distribute the u to the 1/2 through it. And then the last term of u plus 1 squared is just a plus 1 times the u to the 1/2 ought to be plus u to the 1/2. Everybody good with that too? I know I did 2 different distributings there at once, but
Where did that 1/2 come again?
this 1/2 out in front?
No, the u to the 1/2 right there.
That's
Yeah.
the square root u.
Oh, okay, thank you.
Yeah. I just, I feel like it's easier to see the distributing if we write it as u to the 1/2 rather than square root u. Any other questions on how we got to this as our integral? All right, so now we've got 1/2 of the integral of u to the 5/2, which should be what?
2/7 u to the 7/2.
2/7 u to the 7/2. And then what about 2u to the 3/2? That should become what?
2/5 u to the power of 5/2.
Don't forget times the 2. So that's
Yeah.
4/5 u to the 5/2. And then that last one should become what?
2/3 u to the power of 3/2.
I should write mine plus a constant. And so now we'll just distribute the 1/2 through and replace all the u's with x squared minus 1s, and we're done. So half of 2/7 is 1/7. So 1/7 x squared minus 1 to the 7/2. Half of 4/5 is 2/5. X squared minus 1 to the 5/2. And half of 2/3 is 1/3. X squared minus 1 to the 3/2 plus that constant. And that's it. Good or no?
good.
Anybody have any questions on any of the integrals we have done so far?